There we go. So wait, we got audio now. Okay. All right. So are there any questions about the homework assignment that's due on Thursday? Yep. Any question other than why is it so easy? Well, it's only easy if you figure out a way to do it mechanically, which is kind of the idea behind the homework assignment, is to make you guys kind of think about it, do it a few times, go like, well, this is so mechanical, I think I can come up with a mechanical way to get this done so that I don't have to waste, half an hour to get it done. I can use the half hour to write a script instead to get it done. Yep.
Come exam time, is this something that you might actually test us on now?
No, not this one. Because with this one, I just want you guys to get used to the flags to basically figure out, okay, how the flags relate to the operations. In this case, it's subtraction, which is subtraction, because subtraction in particular is important. Addition is kind of good too, it's kind of useful, but subtraction is even more important. Okay. And everything ties into how numbers are represented. Okay, so we are now in the signed number topic, and we are basically talking about subtracting and comparing, and how the various flags are useful in a comparison. Okay, so let's do a quick recap on the various flags. Okay, so we have the sign flag. Okay, the sign flag is nothing more than the most significant bit of the result of an operation. And when we talk about an operation, we are talking about mostly addition and subtraction.
Oh. Okay.
Yeah.
I just realized that it's when the assignment ended, but I was finished, and I was like, oh my god.
No, it's due on Thursday for this class.
I was thinking the same thing.
Yeah.
Okay, so we also talked about the other flags. The Z flag is also easy, right? The Z flag is a 1 if and only if the result of an operation gives you a 0. Okay, so the way you come up with a gate to do the Z flag is you feed all the bits of the result of an operation to a NOR gate, so that if all the bits are all zeros, then the output of the NOR gate is going to be a 1. So that's how we derive the Z flag. The carry flag is really just the carry, okay? It's the final carry of an addition or the final borrow of a subtraction. So those two are, we're familiar with already. So what is left, or a little bit harder to understand, is the overflow flag. The way to look at the overflow flag, there are two ways to look at it. One is to look at it, using the meaning of the flag, which basically means the width of the numbers is not enough to store a number, but only when you look at the numbers or when you look at values in a signed way. Okay, so the overflow flag only applies when you need to look at things in a signed way. But when you look at it from the bit perspective or mechanical perspective, this is how we see it. Okay, so we'll take a look at the derivation first. Did anyone download the updated ALU? Because the updated ALU actually has all the flags implemented as gates already. So if you look at that one, it actually shows you how everything is done. So before we do that, I'm going to give you guys a quick overview of what the overflow flag is. Okay, so in an addition, okay, so let's take a look at an addition here. So we're going to say we're adding this 4-bit number, A blah 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 plus B blah blah blah, and we end up with a result. I don't even care about all the other flags, so I just end up with a result of C blah blah blah. In other words, the carry bits all in between and all the other stuff does not even matter, because as a 4-bit number, A, B, and C are basically bit 3 of each number, which is the most significant bit, which is also known as the sign bit, okay, which indicates the sign of the number. If A is a 1, it means the number is negative, or it represents a value that is negative. Okay, if A is 0, it means the bit pattern is representing a non-negative value. Okay, so when in an addition, overflow is basically saying if I'm adding two numbers that are negative, but somehow I end up with a number that is non-negative, we have an overflow situation. Is that okay? Can everybody read A and B and not C? This is using the shorthand that we have been using for a little bit in this class. So A is 1, B is 1, C is a 0 will make this particular conjunction true, and that is a situation when you have an overflow, because it means that when you're after adding two negative values, you end up with a non-negative value. Not a very good situation. Yep.
So those two ones are negative when you're adding to A.
The sign flag, when you have a 1, it means that the value they are representing is negative.
Okay.
But that is the result of choosing to use 2's complement as negation. Okay, but there's a situation where you have a not A, not B, and then a C. That is also an overflow, because in this case A is a 0, B is a 0, which means we're adding two non-negative values. But somehow C is a 1, which means we end up with a negative value. So if you add two non-negative values, but the sum is negative, then we have a problem as well. We have an overflow situation. Okay. Subtraction works about the same way, just slightly differently. Okay, so we have A blah 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 minus B blah 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 blah, and then we end up with C blah blah blah. Okay. So in this case, in the subtraction, the overflow flag is basically saying if you subtract a non-negative value from a negative value, but somehow you end up with a non-negative value, then we have an overflow. Is that making any sense? You start with a negative value, which is A is 1, but then you have a non-negative value to subtract from that number, which is not B, and then you end up with a non-negative value, which is not C. It doesn't make any sense, right? Because when you subtract a non-negative value from a negative value, the result should always be negative. But if it is not negative, that means you end up with a result that cannot be represented in 4 bits anymore as a signed value. Is that okay? But there's also a kind of mirror of this particular situation, which is not A, B, C. Whoops. There we go. Which is basically saying you start with a non-negative value, you subtract a negative value from it. So the difference should still be non-negative, because you're subtracting a negative value, which is adding a value to the original one. But somehow you end up with a negative value. Okay? So all of these cases are covered in your homework assignment. Your homework assignment, the random number generator is not just all random. There's an offset of A plus. Okay, if you look at the actual formulae, of the cells, there's an A plus in certain cases, which basically forces all the possible situations to happen. So you should encounter all of these situations. Is that okay so far? Okay. All right. But this is great, because can I implement this in logic gates? Remember, the plus is not a arithmetic plus; it is a logical OR.
Yes, you can.
Yep, this is a DNF, right? It's a disjunctive normal form, and so is this one. So both of these can be done using just logic gates. Okay, so now that we know that all of these flags can be done with logic gates, let me just kind of quickly go back to control unit, so I can just re-download the updated ALU and show you what the ALU looks like at this point. Some of you did that already, because you just took a look earlier. Okay, there we go. So this is the one, and the ALU it actually doesn't look like this anymore, but I was too lazy to update the picture, so I did not update the picture. But the actual design has been updated. So I'm going to download this again, replace the one that I have already, and we'll go take a quick look at that. Okay, this is my recorder screen. There we go. And it downloads ALU. There we go. Alright, so this is the new ALU, which is based on the other ALU with some stuff added to it. Okay, so we'll take a look at the stuff that is added to it. We'll start with, last time I already talked about what is a tunnel. Okay, this is called a tunnel. And the purpose of a tunnel is basically it's a wormhole. Okay, so just kind of imagine Los Angeles traffic jam, right? Okay, you have the on-ramp, the off-ramp, the intersections and stuff like that. And that's all because of, you can only do so much routing in two-dimensional space. Okay, and all those, pass over and stuff like that, that's equivalent to a multi-layer circuit board without the vias, because you cannot go through the vias and just drop several levels down to a surface street from the highway, right? Okay, so, but there's only so much you can do with all that stuff. And for those of you who grew up around Sacramento and think that we have really, really bad traffic problems and we have already really convoluted highway ramps and whatnot, let's take a look at some around the Los Angeles area.
San Francisco is bad traffic.
Well, San Francisco is bad in terms of traffic jam, but in terms of the on ramps and the off ramps, how to connect one highway to the other highway, San Francisco is not bad. Highway over.
City,
So we'll
down every street.
we want an overview, like a.
Yeah.
This is kind of bad, but not really super bad.
You want to type highway overpass because it's going to bring all the overpasses. So if you do highway overview, it should give you a map of the layout.
Overview.
Yeah. There you go. Say satellite.
There we go. So look at that. Okay, that's pretty bad. I think we find something like this in the Bay Area as well. In San Jose, Santa Clara, they have some really kind of monster interchange similar to this. Okay, so but the whole point of this is if you do not use tunnels in your logic sim design, this is what you end up with. Okay. Which means that if the connections are still there, okay, if you follow the wires, you're still getting to the right connections, but it becomes increasingly difficult for you to track. Where is this going to? Where is that going to? And so on. If you move one component, what happens? All those wires got messed up, right? Which is bad, okay? Because it makes it very difficult to maintain your logic sim design. Okay, so the answer to this problem are these so-called tunnels, okay? But a tunnel is not exactly a tunnel because a tunnel means it is submerged and it emerges on the other side. This is more like a wormhole, okay? Where you go into one end and then poof, you pop out on the other end, okay? So for those of you who don't like the term wormhole, think Stargate, same thing, okay? Is that okay so far with this analogy? Because sometimes with at least some classes, people look at me and go like, what is a wormhole? Where's the worm? Right? And what is a Stargate? Who locks it? So, if you understand those terms, that's basically what it is. So in this case, I'll just kind of zero in and zoom into one particular one. So we have S out or sign out, okay? This is the sign bit as an output. But this is a tunnel, it is not a pin, okay? This is a tunnel, or at least one end of the tunnel, and this is the other end of the tunnel as out, okay? So what we can do is to click it into this emulation mode. In the emulation mode, if you click on the node, it will light up all the other nodes, all the other connections to the same node. So we'll click this one here, come on, click, and you can see how this one is now highlighted, and so are these. Because logically, they are connected to the same node, but they look separated only because I used the concept of a tunnel, which is a logical concept to say that, okay, this is one logical connection, and the same logical connection is connected to here. If I have it down here somewhere, which I do, it's going to be, that part is highlighted as well. So let's move down here a little bit. See how S out is also highlighted here. Even though these wires are not physically, quote unquote, physically connected, they're all connected to the same tunnel. Yep.
Do real circuit boards have this sort of thing, or?
No, real circuit boards do not have these things because we do not have the technology to create micro wormholes.
Okay.
Yeah.
That'd be nice.
But but when it comes to real circuit board, they are usually auto-routed, which means, a program, using, massive amount of processing power is evaluating, a lot of different alternatives to move the wires and go through the different layers and stuff like that. So for the most part, we don't have to do that. So we can just leave it up to the auto router to route the actual traces or the copper on actual circuit boards. Okay, but when you're designing something, you cannot really rely on auto routing because you are the one who's working out the logical connection. The software or the auto router is really just trying to figure out physically how do we connect all these pins that are supposed to be connected together, and it can handle that part. But logically, when we design the circuit, you have to either use a picture like this, or you have to use a programming, quote-unquote, programming language like Verilog or VHDL to just, kind of spell out how things are connected. Okay? How many people are planning to transfer to Berkeley into their EECS program, not CS? Okay. Well, you don't have to raise your hand if you don't want other people to say, oh yeah, Berkeley. But for those of you who are planning to go to Berkeley with the EECS program, the final year project is to design a processor. But they're not going to design a processor like I do here. They're going to use Verilog, which is a quote-unquote programming language. It looks like C, it has loops, it has conditional statements and stuff like that. But the objective is not to actually write a program where the program itself is the processor. You're using a program to generate the connections, the gates and whatnot that becomes the processor. It's called a hardware description language, HDL, hardware description language. Okay, but it serves the same purpose as Logisim, except you can do it in a much more flexible way. In other words, for instance, if you want to replicate a certain gate like 5 times, you just use a for loop. For I equals to 0, I is less than 5, plus I. Create these gates. Okay, when you say I want every bit 0 of these gates to hook up to that multiplexer, there's a descriptive way to do it in a programming language way. So it's very nice in a way because you can come up with these designs with a few lines of code instead of having to lay out everything graphically. But this allows you to actually look at things in a much more spatial way. So for people who are spatial, who like pictures, this is a lot better compared to HDLs. Is that okay so far? All right, so I'm just gonna make this discussion a little bit more complete by pointing to VHDL and also Verilog. Okay, so VHDL is one. This one is a little bit more kind of academic, not used as much in industry. The other one is called Verilog, which is used a lot more in industry. Okay, so you look at VHDL as Ada, as a programming language, and then Verilog is kind of equivalent to C and C++. So one may not be the best programming language, but it is used a lot more in industry. Is that okay so far? Okay, all right. So getting back to our design here, so I got kind of digress a little bit. So getting back to here, we'll focus on specific portions of the circuit. Okay, we'll look at this part here, and this is the circuitry to deal with overflow. Okay, to compute the overflow flag. Can anyone tell what the top one is doing as opposed to what the bottom one is doing? And S out is the sign flag of the result. S1 is the sign flag of the first operand. S2 is the sign flag of the second operand. Yep.
I think it's testing the O flag, and the top one is addition, and the bottom one is subtraction.
That is correct. So this circuitry here is equivalent to the equation that we just looked at for the overflow flag of addition, and then the bottom one is for computing the overflow flag for subtraction. Okay? So how do we get this out of the ALU?
Oh, you're up.
So to get this out of the ALU, we have to, I use a mux here. So this is the overflow flag in. For all the other operations other than addition and subtraction do not affect overflow because it doesn't make any sense to affect overflow when you're doing logical AND, logical OR, and bit shift. So those basically just keep whatever is coming in as the output. But when you're performing addition or subtraction, which is this one and this one, then the mux will select these two as the actual overflow output. The Z flag is easy. The Z flag is actually slightly visible. This is the Z flag. When you look at how the wires goes, it's easy. You just take the output of the entire ALU, you split all those wires into the 8 individual wires, feed all of those into a big NOR gate, and then the output of the NOR gate is the 0 flag output.
So 0, 1. So if 0, 1.
If it is a 0, then the
Yeah,
flag is a
that's the
1.
reference.
Yep. Okay. And then the carry flag and the borrow flag, those are originating from here. Okay, so we have the adder and the subtractor. Out of the adder we have C out of the subtractor we have B out, or carry out and borrow out. And those particular wires are connected down here in this final mux for C out. So with C out, any operation other than addition and subtraction, we will just take whatever the C in is and pass it straight through as a C out. Okay? The ALU itself does not have any register to store these various flags. Okay? So I'm going to have an additional register as a status register to store all of these flags. But the ALU itself does not store. Okay? So whatever you have in, you will just pass it back out because they should not affect the carry flag. But when you are dealing with an addition or subtraction, then you want to use those as your carry out. The selection of all these muxes, okay? So when you look at this dotted thing here, which is the selection, they all hook up to exactly the same pins. They all hook up to the operation selection pins. So out of these 3 bits, okay, we can select 0, 0, 0 is addition, 0, 0, 1 is subtraction, and then 0, well, we can look at the actual gates. I haven't changed that part of the design. So 0, 0, 0 is addition, 0, 0, 1 is addition, subtraction, and then we have bit shift, we have logical not, bitwise not, bitwise and then bitwise or. But other than the addition and the subtraction, the other ones do not affect the carry flag or the overflow flag. The sign flag and the Z flag are affected by all of these operations. Is that okay so far? Yep.
Can you show another multiplexer? There is C out in and C out. The same label name?
C in is a pin coming in.
No. It's on the bottom. On the right side.
Here?
No. Just picture on the right. Okay, Max. See? On the top it's C out in and C out out.
Oh, you're right. Okay, so that may be a problem because they have the same name. So this C out should not be called C out, or this should not be called C out. Because this is the carry out from the adder itself. This is the actual output of the entire thing.
Should you, if you just uppercase one of those letters, it should fix it, right?
Well, we can change one to be like carry flag out, like that. And then we change the ones to carry flag out. Thank you. That's a good point. Good observation there. There we go. Good job. Okay, are there any questions about this? I'm not gonna run this one, in emulation mode because I don't want to promote this as a way to do your homework assignment. Which means I already talked too much. So for those of you who want to explore, use this for a little bit of exploration, okay? So I will save this file just to be sure. Okay, but now that we have, so with all these flags and all these pins, what are we gonna do with these? Do you guys remember conditional branches that we talked about a long time ago? Okay, so these are all gonna be used for conditional branches. In other words, most of the time the program counter is just going to add one to the next instruction, to the next instruction, to the next instruction. But that means you cannot branch. You cannot branch, you cannot have any kind of branch. You cannot even have an infinite loop if you cannot branch, right? So in order to branch, that means sometimes you don't want your program counter to just increment. You want to say, hey, program counter, I want you to become this value so we can continue execution at that location in memory. Okay? You can do unconditional branch by just changing the program counter. But what about conditional branches? How do you implement if statements inside the processor? Well, sometimes you want to go this way, sometimes you may not want to go that way, you want to go the other way. So ultimately, these are the flags, these 4 flags over here, okay? The carry flag, the Z flag, the sign flag, and the overflow flag, these are the ones that will help determine whether we should feed the program counter, just 1 plus the old program counter, or should we feed the program counter something else. So ultimately, these will be connected to the mux selection that goes into, or demux in, going into the program counter. Okay. And I'm not sure whether I have uploaded that one or not. I don't think I did. So I'm just scrolling to the end here because I may not have, I don't think I have uploaded the design that incorporate all of these flags. So that will be available later. So I'm not gonna spend too much time on that today. So we are now back to signed numbers. So now we want to look at these flags here and go like, okay, how do we use these flags to determine whether a comparison ends up with a true or ends up with a false? Because ultimately that's what we want to do. We want to be able to implement everything that you can specify in C and C++ and have some kind of mechanism in the processor to do it. Is that making any sense so far? So far, okay, all right. All right, so let's take a look. I'm switching back to the text editor here, and we'll take a look at something like this. Well, let's start with unsigned, because unsigned is actually easier. Okay, so we have x, y, and if you want to be sure that these are all 8-bit numbers, because we want to make it all fit into our 8-bit architecture, one way to do this is to use okay, I just drew a blank here to specify it. No. There's a way to specify uint8, right? uint8 underscore t. I think that's the universal way across all compilers. There's a header file you have to include to use these specific type names. I think is it stdint.h. Okay, thank you. stdint.h. Okay, thank you. So if you include that include file, it would define uint8, uint16, uint32, uint64, and then on the other side you have int8, int16, int32, and int64, all with an underscore t after that. The objective of these particular types is to make the width of the variable controlled by the programmer. Because when you just say unsigned xy, then my question is, how wide is that integer? Okay, depends on the compiler, exactly. So it depends on the compiler and what platform it is cross-compiling to in some cases. In some cases it's native. If you just use GCC on a 64-bit system, then an unsigned is probably 64-bit, okay? Because it is the default width of your data path. But if you cross-compile, then you have a bigger problem. Because if you can use a 64-bit Linux system and cross-compile to a 16-bit system, so in that case, your cross-compiler is going to say, hey, an unsigned is 16-bit instead of 64-bit. But why is that even important?
Back to the 64-bit computer, the process will still run slowly.
Okay, so there's a speed difference, maybe, okay? But other than that, why is that important?
If you're like testing out an algorithm on your desktop, and then you cross-compile it, suddenly it blows up because you were overflowing. Oh, it works on 64 bits, but then those numbers don't fit.
Exactly. So that is the best description. Okay. So I'll just rephrase that, because I need a recorder to record it as well. So the bottom line is, if you use a 64-bit, integer as an unsigned or signed, doesn't really matter, because in this case, it's just the width of the integer that matters. The range of the number of the 64-bit number is pretty big, okay? It's 2 to the power of 63, depending on whether it's signed or not, you can double that, okay? But it's a pretty big range. So if your calculation involves, let's say, the square of two 16-bit numbers, hey, a 64-bit number can easily handle the square of a 16-bit number, okay? Even a 32-bit integer can handle that, okay? So you develop your program, you test it, with a dry run on a 64-bit platform, it works fine, okay? Everything works fine, your test suite, everything, and the whole thing works. But the moment you port it into the AVR architecture, which is used by the Arduino, things will start to, it will work a little bit, and then it will basically just bomb out, okay? Well, the reason why it's going to bomb out only in certain cases is when you're dealing with numbers that are relatively small, a 16-bit unsigned will still be able to store the square of two 16-bit numbers, okay? As long as the value itself can be contained within 8 bits, you can still use a 16-bit number to contain the square. But when your number gets larger, then the square can no longer be represented using a 16-bit number, then your program starts to break down. Because there's just no way to store the square of a 16-bit number. Is that making any sense? In 16 bits. So now you have a big problem, because on one hand, you test the program on a PC, everything works. But the moment you port it to an embedded system using a smaller processor, it doesn't work anymore. Or it works in some cases, but it doesn't work in other cases. So now you have a bigger problem, because it is much more difficult to debug a program that is running on a robot as opposed to a program that is running on a desktop, and you can just use cout or GDB to debug stuff. Does that make any sense? Does it sound like that I have encountered this problem before?
Possibly.
And I have personally encountered this maybe once or twice, because I used to teach a robotic class at UC Davis. Every year I get this like 2 or 3 times from the teams in that class. And it's all because of the width of the integers. Okay? So that's why it is important, if you want to make sure that your program is portable across architectures, it is important, one, for you as a programmer to figure out what is the correct width of that particular integer. Okay, so you have to think ahead of time and say, okay, what kind of value, what is the range of values that x and y will need to store? Can it be contained within 8 bits? If not, then you ask yourself, can it be contained within 16 bits? If not, can it be contained within 32? If not, can it be contained within 64? So if you use code like this, this code is completely portable to a different architecture, because the cross-compiler will have a different stdint.h or standard integer.h, the header file, and it will define UE64 in a way that it will guarantee that x and y will have 64-bit as the width. Is that okay? So this part does not have a whole lot to do with computer architecture or assembly language programming, but it is still very important when you're dealing with C and C++ programs. Because unlike Java, in C and C++, the width of integers is basically compiler dependent, platform dependent. So you as the programmer will have to kind of take care of that. Okay, but in this case, we'll just deal with 8-bit numbers. So we say specifically x and y are 8-bit numbers. If I say if x is less than y, then blah blah blah, else blah blah blah. Okay, we haven't really talked about how to translate conditional statements into assembly language, because we haven't even talked about assembly language yet. But the question is not even that. The question is just focusing on the comparison and say, okay, with all the stuff that we have talked about at this point, can we determine whether x is less than y or not, using the flags that we have talked about?
Yes.
And if so, which one am I going to use here? And if I know which flag I'm going to use, then should I go to the then branch if that flag is a 1, or should I go to the then branch when that flag is a 0? Okay, so those are the questions that we want to answer. So I'm going to put some columns over here. Okay. The first question is which flag should I patient? Okay. So the first one is which operation, and then which flag, and polarity of the flag. There we go. So we have several columns to fill in here.
If the sign flag is
Okay.
positive.
Well, what operation should I do first? In other words, should I do a bitwise AND, bitwise OR, bitwise NOT, bit shift, addition, or subtraction in this case?
Subtraction.
Subtraction, okay? So we want to perform the subtraction. Now, when I say perform the subtraction, I'm not specifying what to do with the difference. I'm just performing the subtraction itself. It's just going through the subtractor so that we end up with all the bits according to the result. I'm not even going to store the result anywhere. So I'm just going through the same motion as a regular subtraction to set the flags, but I'm not going to store the difference. Okay, so the next question is even more important. Which flag or flags, okay, depending on how you look at this, which flag should I pay attention to after a subtraction of unsigned numbers so that I can see whether x is less than y or not? Which flag would do this?
Overflow sign.
Okay, so we got 4 flags, right? So let's go through the 4 flags. Okay, let's rule out the obvious one. The Z flag can be ruled out, right?
Yeah.
Because the Z flag is only useful when you are looking for 2 values that are identical. Okay, we're not looking for something that's identical, so the Z flag is not going to be very useful.
Sign flag doesn't matter because they're two unsigned numbers.
Exactly, the sign flag does not matter because we're dealing with an unsigned comparison.
Overflow is never triggered.
Overflow is also only applicable to signed numbers because in order to determine the overflow flag, we look at the sign flag of the components, right? So that means it's also signed. It's an operation or it's a flag that relates to signed numbers. What do we have left? The carry / borrow. Okay, very good. So we'll just call it the carry flag, okay, which is also the borrow flag. So now the question is, what do I need the carry flag to be in order to go to the then branch? Okay.
1.
Absolutely. Okay.
1.
If there is a borrow, then we know that x is less than y. Isn't that really the definition of borrow? Is you don't have enough? You don't have enough, then that's why you're borrowing. So if x is not as much as y, then we have to borrow, and as a result, the carry flag is a 1. Yep.
Could you do one more time? So how did you know it was negative again? Because x is less than y? Is that y or?
Okay, rephrase that question, please.
So you have x minus y. I was wondering why it's negative and why is it not?
I don't know whether it's negative. I don't even care because these are unsigned numbers, remember.
Okay.
Unsigned numbers cannot be negative.
Okay.
That's why the sign flag makes no sense, the overflow flag makes no sense automatically. So we are left with the Z flag, which is 0. We are not checking whether they are the same or not. So that leaves us only with a carry flag. But if the carry flag is a 1, I want to perform the then branch because in that case, it indicates that x is less than y. Otherwise, we won't end up with a borrow. So that automatically makes the other case C equals 1. Z equals 0, sorry. There we go. Is that part okay? How we can utilize the 4 flags that we have talked about, in this case just one of them, to help us determine which way to go. Okay, so far? Makes sense? Okay. Next. And do you guys know that if you just have less than, you can use the less than operator plus the other logical operators to emulate any other comparisons. Okay, let's go through the exercise first because I claim that the carry flag is the only thing you need to know when it comes to finding out the result of a unsigned comparison of any kind. Okay, so we'll check out why that is the case. So we'll look at okay, what if you can only have the less than symbol, but also any logical operators, which will include not, or and. Okay. Okay. So the obvious one is just less than. A is less than B is A is less than B. Okay. Well, that's the easy one. How about the other one? A is greater than B. How do I re-express A is greater than B, but only using less than?
Add them and over here.
Just switch the order, right? Isn't that the same thing as saying whether B is less than A? Okay, so we can switch the two sides and still using just less than. Cool. What about A is less than or equal to B? If A is less than or equal to B, then what do we know? How do we convert this one to use just less than? Okay, isn't that just saying that it is not the case that, come on, you guys. It is the same. You're just negating. Okay, it is not the case that B is less than A. It's the same thing as saying A is less than or equal to B. If you're looking at this and go like, I'm not so sure about that, use a number line. Okay, so use a number line to help you visualize. Okay, so when you use a number line, is it working?
It's hella clever. I got it when you said you did it.
Okay. But that makes the other one actually easy too, because if you want to express A is greater than or equal to B, then it's the same thing as, yep, okay, because it's just flipping the order, right? Okay, let's work with something that's even more evil, not equal to B. How do we express not equal to, but only using less than? I made a mistake a little bit earlier. I used the other symbol to mean not equal to in SQL and in some other scripting languages, but then I quickly realized my mistake and switched back to the C++ notation of not equal to. But that should have given away the answer already. Not equal to is also known as less than or greater than. If A does not equal to B, as far as integers are concerned, it means A is less than B or A is greater than B. Does that make any sense? Wait, we know how to do greater than, don't we? Okay, so this whole thing is really just saying that A is less than B or B is less than A.
Oh, so you're allowed to do more than one statement. I was trying to do it with one statement.
No, I did not put that restriction on myself. I said we can use any logical operator. Okay, we have one left, which is equal. Okay, are those two numbers the same?
Yeah.
So how do we do that?
It's not less than B, or it's not less, or A is not less than B.
Okay, lazy as I am, this is what I'm gonna do. Right? Then we look at this and go like, oh, that is convoluted. Fine, let's apply the De Morgan's law, right? So after you apply De Morgan's law, you get something like that. And you look at this and go like, okay, well that looks a little cleaner. Fine. So are we convinced that all you need is just less than? So next time you write a C++ program in CISP 430 or 400 or, well, you should not be taking 360 at this point. So if you write a C program next time and you only use less than symbol, let's check out, what the professor is going to say about your program.
Give me an ad.
Probably.
It's not readable at all.
I don't know. I think Fox did something like this when I took it with him.
It's like it works, but I have no idea why.
Oh, that's
What works?
You wrote it like this on purpose.
If you really did write, which is less than.
Oh, okay. Well, you can always just pound define a macro. You can always just do like pound define less than or greater than. Okay, if whether it's greater than B or not, then you can just define that to be that, right?
Just go through the program.
Yep, yep. Now, the best way to do this is actually to include parentheses because, in case B is an expression
Can't be this.
and A is a longer expression, you always want to use extra parentheses to make sure that whatever A is does not interfere with the rest. Yeah, pound defines, macro definitions in C and C++. It's kind of questionable. Sometimes professors will frown at that and go like, this is only this is what people use in the 60s or 70s, but don't use it anymore. And then some people look at it as a pragmatic and go like, well, it's a practical thing to use in some cases. So in other cases, you say inline, bool, greater than, and then you would basically give it a type. You can always just use a template function as well, so it will work for anything that has the less than symbol defined. Yep.
The inline is when you basically ask the processor.
When you say inline in a C++ function definition, you are suggesting to the compiler and say, oh, let's turn this into quote-unquote a macro so that the code is actually expanded inline instead of an actual function call.
What happens if it doesn't want to? You're suggesting it.
The compiler can always deny your request and say, nope, this is going to be a function. All right, so that means, but this is important, okay? This is important because it means that as long as we know how to determine whether something is less than the other one, we are good, okay? We can implement all of the other type of comparisons just knowing less than, which is great. It is great because now I can just copy and paste this code down here and just ask one more question. What if X and Y are signed, okay? So I'm going to erase the part where we have to rework things because this one is actually significantly harder, okay? Even though it does not seem like it, it is a little bit harder. Okay, so let's answer this question. Which flag should I look at in order to determine when the bits are representing signed values? Which flag should I look at to determine whether X is less than Y and X and Y being signed numbers? Okay, let's rule out the obvious ones. Okay, the first one is the Z flag. Okay, rule that out because Z flag does not determine order. It only determines whether they are the same or not. Okay.
Borrow is not going to help us.
The borrow is not going to help us because we can see that the borrow flag is useful for unsigned, which does not automatically rule it out for signed numbers, but it does not. Okay, so we are left with the signed flag and the overflow flag, right? Okay, so we'll put this question on here. And then we'll go through some examples, okay? But we'll go through some 4-bit examples. So 4-bit examples. And you will see some of these in your homework assignment too, okay? Because your homework assignment cover all of these possible cases as well. Okay, so let's look at some 4-bit examples. And this is signed comparison. So we want to look at values that can be represented as a 4-bit number signed and say, okay, so how do we determine those orders? So let's find out, okay, 1 versus 2. Okay, so I'm just writing down these examples here. Then we have -1, -3, minus -1. Because in every single case, I want the first number to be less than the second number. Okay, and then we can have one number being negative, the other one is not. So we can have a -1 over here, and then the other one is like a 3, okay? -1 is less than 3. And I think I'm missing 1 here.
You got 2 positives, you got 2 negatives, and you got a positive negative.
Yeah, but there's one more. Okay, there is one more.
0?
No, this one is like this. -8 versus 1. So even though it looks like the same as the other one, this one is a little bit special. Okay.
It's going to change the sign flag to 0.
Well, okay. Let's take a look at the result here.
So what
Okay.
of them won't be allowed?
All right. So let's go ahead and perform these operations. So we have 0, 0, 0, 1 minus 0, 0, 1, 0. And then the result is going to be a 1 over here, a 0 over here, a 1 over here, and a 1 over here. Okay. So I want to answer the question, what are the flags? Z flag, easy. Okay, they're all 0 for the Z flag anyway. The borrow flag is going to be a 1, okay, but we know we don't need to look at the borrow flag, or we know that as a carry flag. What about the sign flag? Sign flag is a 1. What about the overflow flag?
0.
Overflow flag is a 0. It makes sense because we subtract a positive value, non-negative value from a non-negative value, we end up with a negative value. The sign makes sense, okay? This is one case where the sign makes sense either way, okay, whether it's positive or negative, it still makes sense. Okay, all right, let's move on to the next one. -3. Okay, how do we represent -3 as a binary number?
Whoa.
0, 0.
Close. That's 1's complement. You have to remember to add 1 to the 1's complement. So it is 1, 1, 0, 1. Okay, so this is 1, 1, 0, 1 because it is the 1's complement plus 1. The 1's complement is 1, 1, 0, 0, but since you have the plus 1 to it, it becomes 1, 1, 0, 1. Okay, so we subtract -1, which is 1, 1, 1, 1 from this, and then the result is, okay, this one I should be able to figure it out by hand too. Okay, that's a 1 here, and then there's a 1 here, there's a 1 here, and that should be a final borrow. Okay, so looking at the flags, Z is 0, that's an easy one. Carry flag is a 1 because the second number, when you look at it as an unsigned number, it is greater than the first one. The sign flag is a 1, and what about the overflow flag?
0.
The overflow flag is a
It's a 0.
It's a 0 because when you subtract a negative quantity from a negative quantity, ending up with a negative quantity, it can happen. Yep.
How did you see it? 1, 1, 1, 1.
How do I get 1, 1, 1, 1?
Yeah, I understood the first one when you used 1 complement and got 1 at the end.
Oh, you mean how? You mean how do I get this one?
Yeah, that should be the right answer.
That's the right answer.
That would be -3.
But this question is how did I get 1, 1, 1, 1, right?
No, that's not that. Different questions.
Oh, different questions. I see. So 1, 1, 1, 1 is the representation of -1.
Right.
How do we know that?
Because we
That should be
provided it.
1,
Sorry?
Right?
By 2's complement or?
By 2's complement, exactly.
That was going.
So how do you apply 2's complement?
Yeah, 1 more.
Well, before you add 1 more, there's one thing to do first. 1's complement, right?
Oh, yeah, right.
Which means you flip all the zeros to 1s and all the 1s into zeros.
Right.
So 0, 0, 0, 1 becomes 1, 1, 1, 0, and then you plus 1 to it, that becomes 1, 1, 1, 1. Yep.
These two examples, the first example, your result -1, but it represent like 1, 1, 0, 1. The second example, -1, represent as 1, 1, 1, 1. It's different
Your answer is
representation
wrong.
of the same
That's,
number.
we have the same question then. Your answer for number 1 is incorrect. The answer is 1, 1, 1, 1, not 1, 1, 0, 1.
That's correct, it is 1, 1, 1, 1.
But the first
The flags.
1
0, 0, 0,
Oh,
1
right, right.
minus
Okay,
0,
gotcha.
0, 1, 0,
Okay,
1.
gotcha. Okay. Because I misread the column here and thought there's a borrow. Okay. Okay. Thank you. Okay. What about this one? -1 is 1, 1, 1, 1. We want to subtract the 3, which is 0, 0, 1, 1, right? But that's an easy subtraction.
1, 1, 0, 0.
Yep. So we got a 1, 1, 0, 0. Look at all the flags. 0 flag is a 0. Carry flag is a 0. Okay, because it doesn't have any borrow. The sign flag is a 1, and then the overflow flag is a 0. It's okay. Okay, if you subtract a non-negative quantity from a negative quantity, ending up with a negative quantity, the sign is okay, not a problem. Are we still doing okay so far with these particular examples? Okay, we got the last one. I think there's one more case I have to. Yeah, there's one more case here actually. So I'm going to add one more test case here. The last test case is something like 7 minus -1. Okay, because that one is actually important too. There we go. So we look at the actual representation. -8 is represented by 1, 0, 0, 0. And 1 is easy. It's just 0, 0, 0, 1. You perform the subtraction. You get 0, 1, 1, 1. Right? So Z is 0. As I said, they all should be 0 for the 0 flag. The carry flag is going to be 0 too, because 1 is not greater than 1, 0, 0, 0 in an unsigned interpretation. The sign flag in this case is a 0, but the overflow flag is a 1. Okay, because you are subtracting a non-negative quantity from a negative quantity. You should always end up with a negative quantity, but somehow we ended up with a non-negative quantity, and that's why the overflow flag is a 1. And then the last one is this guy here. So we got 0, 1, 1, 1 as 7. We subtract 1 from it, or -1, so it's 1, 1, 1, 1. So we want to figure out what is the actual answer. That one is pretty easy, right? Because 1 minus 1 is a 0, 1 minus 1 is a 0, 1 minus 1 is a 0, 0 minus 1 is a 1 with a borrow. Okay, so let's set all the other flags accordingly. We got 0 flag being a 0, the carry flag being a 1, right? Because we have a final borrow. We have the sign flag being a sign flag is a 1. Nope. Did I make a mistake? Sign flag is a 1, and then the overflow is a 1. It's a 1 as well. Now 7 minus -1 is a little bit special because the first quantity is not less than the second quantity, but it is important to describe the flags. All right. So if you just look at all these flags here, do you see a single flag that can be used to indicate whether the first number, the top number, is less than the second number? We look at it. The 0 flag is always 0. Okay, that makes sense because they're not the same. The carry flag obviously cannot do it, right? Because the first 4 cases has the first number being being less than the second number, and then you can see, hey, this is 1 and those are 0s. But what about the flags that are specifically designed for signed numbers? Even those do not work. The sign flag almost get it done, except for this one. Okay? The overflow flag almost get it done if you just say that if it's a 0, the first number is less than, except for the last one. Doesn't work. So what is happening here? Yep. Then how do you want to combine the sign flag and the overflow flag?
You always want S and O to be opposite.
To be opposite, very good. And there's a particular name to specify that.
S not O.
Exclusive OR? If you take the exclusive OR between the sign flag and the overflow flag, that result indicates whether the first number is less than the second number. In other words, we define it.
What about the last case when I wrote 1?
The last one is okay because 7 is really not less than -1. So the exclusive OR is also giving you the same result because one exclusive OR 1 is a 0. Okay, so we'll add one more row to all of these things here. So we'll say the L flag in this case is a 1 because it is by definition the exclusive OR between the sign flag and the overflow flag. This one is a 1 as well because they are different. This one is a 1, 2. This one is a 1, 2. This one is a 0. Yep.
What does it mean by L?
It's just a new
Less than.
Less than. Oh, okay.
But less than in a signed way. So L is only useful for comparing signed numbers or signed values. By the way, this, other than the examples, all of this discussion is in the notes too. Just presented in a slightly different way. Is it recorded? It's being recorded. Let's see. Looks like it's still getting recorded. And looks like the audio is still going, so we are good. There you go. So are we doing okay so far with signed comparison? Okay. So if I go back to my Logisim picture, okay, if you really want to use the result for comparing, it makes sense to combine the sign flag and the overflow flag into the L flag or the less than flag, so that we just look at one single flag so that we can decide, okay, should we branch or not? Because by themselves, each one, okay, the sign flag or the overflow flag by itself is not useful. It's only when they're combined through an exclusive OR, then it becomes useful.
Would that be one of the standard flags in a processor for stuff?
I'm trying to think of different architectures, and the answer is yes. Okay, are there any questions about this part here? Any questions? No questions. Okay. If there are no questions, let me check my notes, because I want to see if I had the overall design somewhere uploaded here. No, I don't. We have the new ALU, and then we have the new register bank, but not the overall processor.
Is it in your CPU designs ALU? On the left side, control unit? Down at the bottom. Up, right there. The grayed out
Here?
executables under the control unit section on the left.
Oh, you mean here?
Is it actually, is the updated one?
No, that one doesn't. That's not updated. That's the old one. I had it done already. I didn't upload it because there was no particular place to upload this one to. That's okay. We can do it this way. Okay. So this is the new updated ALU. Okay, after fixing that particular one. So now the question is, in the overall design, how do we make use of these things so that we can determine where to go in terms of the PC, the program counter? So, okay, this is what we'll do. We'll go ahead and make a new file. I'm just going to create it right now on the fly. Okay. All right. So we'll go ahead and We'll go ahead and add inside my downloads folder ALU as one of the library parts, and it will also load the other one, which is register bank, as the other one. Okay. So now I can utilize an ALU as well as a register bank. So these are almost the same as before, but they are simplified because certain things do not really need to be spelled out the way they were. Okay, but the flags are the important part. Okay, the program counter inside the processor, which is the address in memory of the next instruction, that's usually auto-incremented. So let's go ahead and make the auto-incrementing program counter. Because what I want to illustrate is how these flags are actually utilized in the processor so that we can determine, which way to go. So we'll go to memory, specify a register. This is an 8-bit register. It is my program counter. And then we go to arithmetic, specify an adder so that we can have an auto increment mechanism. Okay, so this goes here, and then we specify a constant of 0. Well, constant of 1 to go into the carry, and then a constant of 0 to go into the second number. go. Now, by the way, there's a different way to do this too. If you want to alter the program counter, one way to do it is to change the whole program counter and say, hey, this is a new value, okay, and that comes from somewhere else. But another way to do this is to be able to specify something other than 0 when to change the program counter. Okay? But I'm not going to go that route at this point. So normally, you want to just auto increment. So normally, I'm not going to connect all the wires necessary to make this work. I'm just going to connect the usual wires to make this just to make it make sense. Okay. So normally, this is what we want to do. Normally, we just want to point to the next location, the next location, the next location, and the output of the program counter typically somehow connects to the address bus, because we want to use the program counter to specify a location in memory and say, okay, hey processor, this is the next instruction to execute. So that's why the program counter has a path to connect to the address bus, but it's not connected directly to the address bus because there are other things that we also want to connect to the address bus. So it has to go through a multiplexer before getting onto the address bus. But that part is not even important at this point. What is important is we want a way to also connect one of the outputs of the registers and say, hey, occasionally I want to use one of these two. I'm just going to pick out one here and say, hey, we want this to hook up to the program counter as well. What is wrong with this picture?
Can't do that.
Wires feeding
So bus fight.
You can end up with a bus fight, right?
You can do a gate to fix that.
You can do a multiplexer, okay? Because a multiplexer has multiple in and one out, right? You can select which one.
Control the multiplexer.
You have to control the multiplexer, exactly. So, but I first want to address the problem that we have here, because the registers, as long as you have this EN on under the out one, then the register bank will try to drive this wire or this particular node, right? The adder is always driving the same node. And if the values are different, then you end up with a bus fight. So you can't just hook it up like this, okay? So this won't work. Well, if it won't work, then it's easy. We just say, okay, get rid of the actual connection, and then we go to the plexers and find ourselves a multiplexer, like so. And we just have to adjust the data bits of the multiplexer to fit the PC. And then the auto-adding mechanism goes to one end of the multiplexer, and then the other one goes to the other end of the multiplexer. Problem solved, right?
And then you use the L flag to determine which one you're selecting.
Well, okay, that's the fun part. Okay, so the fun part now is how do we utilize the ALU or the flags out of the ALU? Those usually would be stored in a register all by itself too. But let's assume that we don't even use a register to store it. Okay, how do we utilize the flags to determine, should I just go on to the next location, or should I let my register output one to determine where I should go next in terms of program execution? Is that okay? So the way it is right now, you can implement infinite loops already, because there is a way to change the program counter to go back to an earlier location. So as it is right now, we can do infinite loops, but not any type of conditional branch. Because we cannot say, hey, sometimes we want to go this way, sometimes we want to go that way. There's no way to select based on a condition. Okay. So what we do is we take flags out, okay, which is this one here. So let's go ahead and hook up a wire here. And then we say, let's hook this up to the selection pin here, so that we can use it. Let's see what's going to happen. Ding! No, it's not going to work.
You gotta
Because
connect it to
the adder.
a C out on the adder. You gotta connect it to a C out on the adder.
that's okay.
That's not what he's
That's
talking
part of the
about.
problem, but that's not the problem that I want to illustrate.
was
Okay,
illustrating
so
the
the
bits.
selection pin goes out here and go up to here. Same kind of thing with you stream, because
How do you turn 1 bit into 8
we have a
bits?
problem, because flags out is a 4-bit output. Okay, because we got the C, Z, O as
Yeah,
flag,
splitter.
right?
It's a splitter.
And then we have only one flag over here. So we go like,
Twitter, and you only
which one should I use to determine which way to go, right? Is that making any sense? Okay. So we just say, okay, that's not going to work. Well, okay. One really bad way to fix this is to go to the multiplexer and go like, that would do it. Right? No, that's not the right way to fix it, okay? We still only have 2 ways to feed into the program counter. So having the 1-bit selection bit for the multiplexer makes sense, okay? So what we need to do is to go to these 4 bits coming out of flags out and say, which one of these do I want to use, okay? Okay.
That makes it harder because then you have to have something that controls the selection of which one you send.
Yes, okay, but let's see what we can do about this one, okay? So let's go ahead and use a demultiplexer. In this case, it's a 1-bit demultiplexer. And we're gonna, nope, it's still a multiplexer, sorry. It's still a multiplexer because we have multiple in and 1 out. Okay, so we already know what the out is gonna go, so that's not the problem. Okay, that's the easy part, right? So what is going into this multiplexer? In other words, what are the possible things that can help me determine which way to go? Should I use one of the output of the register bank to determine the next location to execute, or should I just move on to the next location, auto increment? Okay, so we look at this and go like, hey, there are too many bits here to fit into here, right? So the first thing we need to do is to take this, okay, take just that wire, and split it into the pins that we need. Okay, so we split it as a 4 out. That's fine. Okay, this is perfect. Okay, and then we have to look at this design here and go like, we'll need 2 bits as the selection bit, right? Because we need 2 to select one of 4. But I'm gonna do 3. Okay, and it becomes kind of obvious why I want 3 in this case. Okay, all right. So we'll hook it up and let's see what am I gonna do here to make it look nicer. Okay. All right, so that should make it look a little nicer. There we go. There we go. Here and here. Now, when we have the L flag, there will be one more, okay? So, but since I do not have the L flag in the ALU at this point, it's not available. So now you go like, but what about the other 4 input to this particular mux? I mean, what are we going to feed those? Well, these are all conditional branches, aren't they? Because they're all dependent on how the flags are set based on the previous operation in the ALU. What if I want a unconditional branch? What if I want to feed a 0 all the time? So there's an unconditional branch. What if I just want to move on to the next one, which is always a 1? Well, we can fix all of those problems by using constants.
Which you already have set up.
Yeah, you already have constants.
You already have a constant. Just
You don't have to. You can write that same constant.
You want to look. You want
I have a 1, but not a 0. So I'm just going to specify 1 here and 0 here.
Other constant, not this constant.
Oops. There we go. All right, so we have 6 inputs now into the mux, okay? 4 of these are conditional because they depend on the result of the computation in the ALU. The other 2 are constants. One is just always 1, the other one is always 0, okay? How you want to order these bits is kind of arbitrary, okay? So now the biggest question is, then who controls this? What do you think? I mean, this is the input. This is an input into the mux, right? So it has to match the output of something. What do you think that something is going to be? We have seen that design already. It's completely missing in this particular picture, but it is a very integral and important part of a processor.
memory.
The register.
Okay, we have instruments now in the orchestra, right? We got one instrument here, we got another instrument here, we got one instrument here.
The ROM chip.
Exactly, and the ROM chip.
I meant wrong when I said register.
That's what I meant.
Call that the-
memory.
When you
call it the music box. Exactly.
Oh, I see what you're saying.
So the music box is missing entirely from this picture, but the music box is what is going to drive this particular wire. So the music box will decode an instruction, and after decoding an instruction, it will execute what we call microcode. And as part of the microcode, these bits will be specified so that we will make the right selection to use the right kind of input to determine how we want to change the program counter. Yep.
How would we know where to look in ROM when we controlling that?
Okay, that's kind of a preview of what we're gonna do. Okay, but I can give you a quick description. We're kind of running out of time today, but in 3 minutes I can give you a quick preview. Okay, so the way the ROM is going to be organized in your music box, okay, is going to be like this. So it will, each instruction has a block of memory location allocated to it. Okay, so when you look at an instruction, you will basically use the bits of an instruction to help you index into one of these specific blocks for that instruction.
Oh, I see.
But within the block of that particular instruction, you will execute the microcode. So each microcode is just one location in the ROM chip of your music box. This is going to be pretty wide, okay? Probably 20 to 30 bit wide, okay? Each bit is going into, you know, one of these things over here, 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 to control the various components in the processor. So when you execute a conditional branch instruction, one single slice of the code here is going to control this selector pin here, so that your mux would know, okay, this is a instruction that should depend on the carry flag to determine whether we should just move on to the next instruction or go to whatever the register is telling me to go to. But this picture is incomplete because at this point I just want to draw the connection between flags out to the mechanism to control where we're going to go as the next instruction to execute. Yep.
Isn't the problem though with ROM, it's only write once?
Yes.
Will we ever use memory, like RAM for this?
Well, okay, there are two pieces. This is the music box, which is stored in ROM. Now, not all processors actually store the microcode in ROM, but most do, okay? Because most do not anticipate people to rewrite the microcode, you know, on the fly when you're running your programs. But this is just the microcode. There's another separate piece, the RAM, that is separate from the music box, that is actually your main memory. In other words, this part here, which is your microcode, is a part of your processor. This is actually integral to the processor itself, but there's a much bigger RAM, like 4 gigs, 16 gigs of space, that is completely outside of the processor, and that's not in the picture yet. And that's also where the programs are stored. Is that okay so far? Just the general idea of how things are connected and how the flags that we have talked about at this point in this class, how that is also integrated into the processor design. So in the next class on Thursday, I'm going to upload my updated processor design with all of this stuff here to Moodle, so that you guys can actually see how all the different wires are connected. Okay, and then at some point we'll start to specify the microcode so that we can actually execute instructions. We can compare. We can say, oh, okay, stay in this loop as long as x is less than 5, but exit after that. Okay, so we'll write some very simple code like that using our toy processor, and then we'll move on to the actual Intel processor to talk about assembly language programming. Okay, so the class is progressing. Okay, just differently compared to last semester.
More quickly or less quickly?
Just differently.
So can RAM send a program into there, and then the program tells the microcode we want to compare?
Yeah, it's called the virus. The RAM is actually is feeding, what is missing here is the instruction register. The instruction register decodes into a microcode program counter to execute this code. So you have a program inside the processor to execute programs stored in RAM.
That's the point. That's the thing I was missing. I'm like, so how do you tell it to execute that microcode?
Right.
And that's how you do it.